Okay, what I'd like to do now is to talk about you know, uh, spend this week sort of talking about some other machine learning methods. Again, we've spent a lot of time on logistic regression. We spent time on, you know, uh, linear regression. We've talked about nearest neighbor methods. There are a lot of different machine learning algorithms out there, and it's the I guess the questions that I think are important is it's important to kind of know why there are different machine learning methods. Part of it is that there's just sort of a bunch of clever ideas that can be applied. But the methods presumably differ in certain things. They differ in how expressible they are, how complicated a model you can build with it. They differ in interpretability. Okay, when you have a model like this, would you rather could you figure out what the what the important features are and what it's telling you? They differ based on how easy they are for a relatively inexperienced user to get something interesting out of it. Something like deep learning, there's a certain magic component to it that kind of the more experience you have, the better at it you get. So that's a thing to keep in mind. Then there is a trade-off between how fast it trains and how fast it makes predictions. Different methods exhibit different performance. So when I was writing the book, the textbook, I went and asked a bunch of knowledgeable people to kind of score all the following deep learning methods based on these different criteria. Now, linear regression is the method we've spoken about. Linear/logistic regression is the method that we've spoken about most in here. And the important thing to see is that in many dimensions, it's extremely good. Okay, the only thing that is kind of a limitation of linear regression is that it is hard to express, complicated models in it. You have to add your own nonlinear features, and adding what are the right nonlinear features to something can be complicated. Okay? Any questions about that? So I don't think that linear regression is a shameful thing, especially if you're going to use nonlinear features, okay, where appropriate. That said, nearest neighbor methods, which we talked about, have the property that you don't actually have to do any training at all, essentially. Okay, that they still are, are generally good. I would probably say they're actually. I would have given this a higher score. The main problem with nearest neighboring methods is it's actually expensive to make a prediction. Okay, deep learning methods and kind of some of the other fancier models. These things have a lot of expression. Have the power to create very rich, high dimensional models. The trouble being that they are hard to interpret, hard to for normal people to use, and can be expensive to train. Okay, any questions about that? Then are a bunch of kind of classical machine learning methods, which I do want to talk about over the next couple of days, because these are kind of naive Bayes, decision trees, and support vector machines, because these are techniques that, kind of are useful ways to build, richer models on, modest sized data sets, which I still think is the bulk of the work people do in modeling. Okay, and so that's what I'm hoping to do this week, is to kind of talk about these kind of methods. Any questions about that? Any complaints or any other opinions about any of these machine learning methods? We can open up a floor to discussion if there is some. Okay, so as I was saying, when you look at these machine learning methods, one of the things that should come home to you is that the comparative advantages of many of them are somewhat murky. I notice on many projects, and certainly on the homeworks, many of you saw there was some kind of Python library call you made that could not only test linear regression, but called all these 4 or 5 different machine learning methods. And it gave you the results of classifiers for all of them. And when you did that, what you found was that they all did about the same. It was not like one was generally wildly better than the other. Okay, again, if other people have different experiences, I'm happy to, have a discussion here. But there is a kind of, well-known theorem, okay, in machine learning. They call it the no free lunch theorem. That is kind of a proof that there is no single machine learning method that works best in all cases. Okay, and this does encourage people to try many, many different methods on their data set. That usually doesn't work too well. It does also encourage people to learn one of the methods, at least 1 or 2 methods really well, okay, and get a lot of experience with that. And then they can, get good at making models with that method. Any questions about that? Okay. So the reason you need things that are nonlinear classifiers, okay, or nonlinear classifiers or nonlinear regression functions, of course, is that not everything is linear. And there is kind of a famous example of things that, what is an example of a relatively simple function you can't, kind of fit with a single linear classifier. Suppose your data fell into 2 classes, the blue points and the orange points. Okay, this is kind of an exclusive OR function. The blue region means, it basically means that either X is high and, again, what is the X region? Either both of them are high or both of them are low. If one of them is high, that's not blue. If the other one is high, that's not blue. That's not blue. Okay. So you can't find a good fitting line for this. If you wanted to try to do a classification using the nearest of an XOR type problem, you need something nonlinear. Nearest neighbor methods actually would tend to do good if you had some examples of things. Okay, it would probably come up with decision boundaries that are, can have a shape like this. Okay, but certainly linear regression isn't going to do it. Any questions? Again, if you try to look at this example of an exclusive OR thing where there were 2 classes in these 2 clusters, there is no line that can fit this data, okay, where you can separate the red points from the blue points. So a linear decision boundary is doomed to failure. Other methods that can build more complicated decision boundaries, okay, can successfully recognize these points. And the classic example of such a method would be a decision tree. What is a decision tree? A decision tree is a rooted tree where at every node in the tree we have a test on one of the variables. Okay, and based on this test, if it's a binary test, there's going to be 2 descendants. Okay, and in order to classify a particular example, we walk down the tree and ask basically what it is, do its test. Suppose we have a point, 1, 1. Is X greater than 0? Yes, so we would go down this thing. Is Y greater than 0? Yes, so it would be in class 1. Okay. Does everybody see that if we have a set of numerical values, we can turn it into a binary test, each variable into a binary test, by saying, is it above or below a threshold? Okay. The idea of the decision tree is we have a rooted tree. The leaves represent classes. Okay. And any particular example is going to have a path from root to leaf, and that's going to be how we classify it. Any questions? The important thing to see here is that the decision tree has no trouble at all with this the XOR boundary. If we test, is x greater than or equal to if x is greater than 0, the answer is we're down here. Testing now whether y is greater than or 0. On this side, everything is going to be in class 1. On this side, everything is in class 2. If we now look on the other side of this boundary, again, if we happen to do the test of y equals 0, if y is greater than 0, we say that it's class 2. Otherwise, we say that it's class 1. Any questions? Should be clear that exclusive OR is hard for linear classifiers, but there certainly exist simple decision tree models that can do it. Any questions about decision trees? So what is an example again of a decision tree? Again, as I said before, a decision tree is a world where every example travels a unique root to leaf path to classification. Okay. The goal is that our decision tree partition the training examples into groups that are relatively uniform. You don't necessarily want every you don't necessarily want every leaf to represent only elements of a particular class, but you want them to be, enriched by one of the classes enough that we're going to make the decision to call anything that reaches that node. Okay, the majority label. Okay, and again, if we don't want a world where we have a big complicated tree where every leaf node represents one example, that's the kind of a thing that tends to get overfit, too specialized to its training data. Okay, any questions? Here is a decision tree for who survived the Titanic disaster. You remember the Titanic? Who survived the Titanic? Kate Winslet survived the Titanic. Okay, Leonardo DiCaprio didn't survive the Titanic disaster. That was a ship that hit the iceberg. Okay, what was this decision tree saying? The root node here is saying, was the passenger a male or a female? Back in those days, the lifeboats were supposed to go to women and children first. If the person was not a male, this decision tree says they survived. Now, only 73% of the women on the Titanic survived, but that's a majority of what you have there. Okay, that's pretty enriched over a guess. Okay, and so for so basically, what's this saying? 36% of the people on the Titanic were women, and 73% of them survived. That's what the two numbers here are supposed to suggest. If you were not a male, what were your chances of surviving? Well, the question is, were you a kid? Remember, it was women and children first. If you were 10 or older, okay, we said only 17% of those people survived. 61% of the passengers were men over 10 years old. We classify them as likely to die. If you were a kid, Does that mean you necessarily survived? The answer is no. It turned out that there was another factor. How many brothers and sisters did you have? Okay. Presumably, if you had more than 3 brothers and sisters, okay, you had plenty of people fighting to get you on the lifeboats. Okay. And 89% of the people who were male, young, and had a lot of brothers and sisters, 89% of them survived. Unfortunately, that was only 2% of the total number of passengers. Otherwise, for the kids, if they didn't have enough brothers and sisters, okay, they had only a 5% chance of survival. Okay, any questions about that? The total population in this statistic, the total population of examples is given by here, and that should add up to to the 100, and the enrichment at each node. Okay, originally, if we didn't know anything, we would say there's a 50-50 chance of you surviving, or whatever the survival probability was on the ship. It was presumably less than 50%. Okay, any questions? The goal of a decision tree is to partition the examples so that the leaf nodes represent relatively pure percentages. Okay, either very, very big numbers, meaning they're almost certain to survive, or very, very small numbers, meaning they're almost certain to have died. Any question about what the decision tree?
Yes.
What?
So I'm just trying to think, going back to the machine learning zoo topic earlier, how would you decide for something versus a decision tree or just nearest neighbors classifier? Like, is there some,
Well, okay,
I know
so
we said that.
trees, okay, so what do I think? So decision trees, if we're comparing decision trees to nearest neighbor classifiers, decision trees tend to be very, very fast. Okay, if you think about how you're going to make a classification, is this person going to survive? It is just a walk down the tree. Does everybody see that? What would be, in our dream, what would be the height of this tree if we have n different classes or n different leaves?
Log in.
In a dream, we would have a fairly balanced classifier, and it would be only log n comparisons to make that decision, right? That's not always the way we want to do it, but it should be clear that that's wildly different. That's log of the number of leaves, which has nothing to do with the number of examples. How many examples were there on the Titanic? Let's say we were doing this on the Titanic. How many people were on the Titanic? I think it was something like about 2,000 or something like that, 2,000, 3,000. Okay. Note that the tree is very, very small, and the time it's proportional to the height of the tree, which is something we can kind of control. So the good thing about decision trees are that over nearest neighbor is that it is easy to that it can be fast to make decisions. It also should be clear that it's fairly explainable. Does everybody understand what this tree means? I can interpret this, I didn't need to see the movie Titanic, but I can interpret what this what this tree means, right? It's telling me, does it jive with me? Again, the women survived, the young kids survived, okay? And unfortunately, it made a difference whether they had brothers and sisters. But if you were an older male, forget about it. You went down with the ship. So what's good about the decision trees are that they are explainable. Okay? They tend to be actually, as we will see, can be made to be pretty accurate. Okay? Note that the explainability of a decision tree like this is different than a nearest neighbor classifier. Okay? In a nearest neighbor classifier, would they have said, is Skeena going to, you wanted to say, is Skeena going to survive on the Titanic? You would say, well, what's its nearest neighbor? Okay, and you'd say, well, his nearest neighbor is Leonardo DiCaprio. It's what he's most similar to. And Leonardo died on the Titanic. Okay, so there's a different kind of explainability. One is in terms of understanding the examples. The other is in terms of understanding the features. And I would say decision trees, understanding the features is probably even better than understanding, what were examples that you're similar to. Any questions? Okay, never mind that. So what are the good things about decision trees? Well, one is that they will create very nonlinear decision boundaries. Okay, there's nothing linear about a decision. You're cutting at each variable. You're making a chop at each variable, but then you're making the boundary is kind of a bunch of different variable cuts, as opposed to being a linear combination of the things. So you end up with a nonlinear decision boundary. You don't have to go through any contortions in order to deal with categorical variables. If you wanted to say, if let's say redheads were likely to survive the ship, there is no reason why you couldn't say, is the hair red? Okay, that gives you a binary answer, yes or no. So categorical variables work out just right. Okay, interpretability is a natural thing. Okay, what else is good about decision trees? Well, one tree, gives you some kind of a classification of whether what the label for an entity is. It turns out on any data set we can build a large number of different decision trees. Okay, all of which make efforts at classifying the data set. Now, some trees will be better than other trees, but if you have 1,000 different decision trees, you can now vote and say, what is the majority label? Now, not only do you get a sense of what is the label of the thing, you get a sense of how confident you are. If 999 out of your 1,000 trees said that the guy was going to die, you would be confident he was doomed. Okay. On the other hand, if 50% of the trees said he was going to die, and 50% then you know that they have a fighting chance. Okay. So there are ways you can use multiple trees to give you estimates of confidence, can give you more robust classifiers. Any questions? The final thing that I would say is that you could also use decision tree ideas combining with regression methods, like even linear regression. If you have a world where you have a large amount of data and a large amount of features, okay, you have a huge number of training exams, you want to be able to do it. There's no reason why you couldn't do a regression by building a decision tree classifier. And then let's say you wanted to compute something like how, what their life expectancy, how old they were, long they were likely to live. You could build a regression model, a separate regression model on the examples of each of the leaves. Notice that both the women and the young siblings were both likely to survive. Okay, so their life expectancy was high. But if you wanted to try to predict the life expectancy of these people, it's clear that the kids undoubtedly on average lived longer than the average, well, just because they were younger at the time of the accident. You could build a regression model on the examples. Each leaf represents a set of examples. If you build a separate regression model there, that is a powerful thing. Any questions about that? So why don't people like decision trees? Decision trees are actually very, very good things. I think in machine learning, there's a little bit of sneering at decision trees because it's not really a mathy kind of thing. Machine learning now has a well-developed theory, and this is good. When I look at decision trees compared to something like logistic regression, or naive Bayes, or even deep learning, there is a lack of kind of mathematics there, and I think people, it looks like it's kind of a clumsy thing, okay? But in practice, actually, decision trees are very powerful things. Any questions about that? So how do we build decision trees? Okay, the general way that you would build a decision tree for a data set is in a top-down manner. Originally, you were given n examples, okay? And what you seek to do as the root, you seem to have some test where you want to compare a particular variable against a particular constant, okay? Your goal is going to be to try to find a split. Okay, you have, again, if you have m features, or again, in this case, I guess m is the number of classes. If you have d features for the number of dimensions, for any dimension, if you think about it, if we think of the x value, okay, there's going to be different values. Some of them are going to have positive labels, some of them are going to have negative labels. Coming up with that threshold is identifying where is the label, okay, where you want to say everything on this side goes to one end of the tree, everything on this side goes to the other. There are two different issues when you're trying to identify a threshold for a variable. You might seek a pure split. A pure split is something like this. On one side, all three of these examples are positive, okay? On the other side, it's a mix of things. Alternately, you might want to make a split where it is more balanced. Let me put down just to make it the way I want it. Let's say, let me put something like that. Maybe you would rather have a split something like over here. Sorry. Here, if we have a split here, the number of examples is roughly the same on each side. That's going to be balanced, okay? We like balanced splits because they're going to lead to fast decision trees. We like pure splits because they're going to lead to accurate decision trees, okay? And, basically, we have a trade-off here. Any questions? Now, how should we judge whether a split is good or not? Okay, there is this notion of entropy, is an information theoretic measure of how much class confusion there is. Okay, the entropy formula said that if we sum up over the number of classes, for each class, there is going to be, in the ith class, there is going to be a fraction, f of I, of the total set of elements. So we know that the sum of fi, or as we go over, I goes from 1 to n, is going to be 1. Okay? If we have a world where at a node we have, let's say, two classes, what is the most confused we can be if we have two classes? I'm going to claim if half of them are of class 1 and half of them are of class 2. If that's true, what does the breakdown look like? The entropy is going to be, it's going to be minus 2, because we're summing this up, times the fraction of being in each class, that's 1/2, times log of 1/2. Okay? So in this case, the entropy is going to be basically, what's the log of 1/2? That's basically going to be minus the log of 2. If it was the log base 2 of 2, it's 1. Okay? This is going to work out to be 1 in the case of, what you call it? In the case of 2 classes, if I've got this right. Yeah, if it was the log base 2 of 1/2, that I believe is going to be minus 1. And so this would be 1. In complete disorder, okay, meaning that all the classes are equally likely to occur, the entropy turns out to be log of the number of classes. If you have perfect order, what happens? Well, if one class, perfect order would be a world where one of the class, all of the elements were of class either 0 or 1, and all the elements were of the same label. If that's true, the fraction of one of these things is going to be 1, the other fraction is 0. For the class that is 0, 0 times the log of whatever is going to be 0. It makes no contribution. For the class that is 1, it is 1 times the log base 2 of 1. What power do we have to raise 2 to get 1? The answer is 0. Okay, and so so this turns out to be 0 times that. The entropy is 0 when they are perfectly ordered, meaning that they are all of the same class. Otherwise, there's the most disorder when the elements are equally distributed among the classes. Any questions? Now, what is a good split criteria? Okay. There are typically, we would like the split to produce as much order as possible. Okay. If we think about it, if we have, what does it mean if we have a good split node? We have a particular set up here. The amount of disorder in it is the entropy of the current things. We're creating 2 subchildren. What we would like is we will rate the quality of something based on how much of an improvement in purity we have made, okay, of the classes in the course of a split. The information gain, okay, is a measure of how much have we reduced the uncertainty after that comparison. The uncertainty is measured by the entropy. After we have done our split, what is our world? Okay, well, if it's a binary split, then there are 2 sets that remain, S1 and S2. Okay, we're going to say what is the essentially average entropy of the 2 remaining classes, weighted by how many elements we have. In an ideal world, we would have split the the elements in half each time, so that S sub I was going to be S over 2. But regardless of how we split it, we want to know what is the entropy of the subsets. The information gain is the old entropy minus the entropies of the new pieces. The more information we gain, the better a split it probably is. Any questions about that? There are other measures of kind of how let's say, pure or impure a partition is, okay? And one of them that they talk about is the Gini impurity, which is basically summing up for each class, what is the product of its frequency minus 1 minus its frequency. Ideally, you get into a world where either one class is extremely large, so 1 minus Fi is small, or you get into a world where the other classes are very, very small, so Fi is small. Okay? Any questions about that? So something like information gain provides a natural way to judge what is the next split to make. I will make the next split to maximize my information gain. Any questions? Now, the easiest algorithm to build a decision tree would be a greedy thing. You start at the root and you find which, you pick a variable to split on. You look for where is the split point that maximizes the information gain, and that becomes your root. That's a perfectly, and then you can proceed recursively on both sides. That's a perfectly reasonable way to build a decision tree. One thing to note is that greedy methods will not necessarily find the best or even a good decision tree. Think back to our exclusive OR example that I talked earlier about. Okay, we saw that there is a beautiful two-level decision tree. If only you make the right first cut. Okay, I guess this would have been an alternately equally good first cut. But how do you know that this cut is good? On this cut, what is the purity of each side? Originally, in the whole set, it looked like we had n over 2 red points and n over 2 blue points. If we made this first cut over here, on the right side of it, we still have half the points red and blue. On the left side, we still have half the points red and blue. There has been exactly 0 information gain if we pick the right first split. Okay? And it's not clear that any other split is going to look a lot better, but certainly the best possible split does not look good by information gain. It's only when you look ahead a little bit to see, if I've done a couple of different splits, how does it look a few levels down, that this decision looks good. So in a very good decision tree algorithm, there has to be some level of look ahead. Okay, actually building the best decision tree for any data set is an NP complete problem. So you can't expect it perfect. This is kind of a heuristic thing, but it should be clear that for certain data sets you need look ahead in order to make a good decision tree. Any questions about that? Okay. So if we do build a tree by a kind of greedy thing, when should we stop? Okay. Well, it should be clear that we could build a tree down to the point that every leaf node is going to be a singleton, okay, or all the elements are going to be of the same class. If we have a tree where all the leaf elements are all of the same class, then we have a world that we will get perfect prediction accuracy on our training set. But it's likely to be very dependent on weirdnesses of the training set, okay? And the trees that you build, if you have a big decision tree, you will overfit it. I know that on the homeworks and some of the project things, I've seen people build horribly overfit decision trees. Much better is to try to build a tree that stops when the information gain at a level is small. Once we hit a node that's completely pure, there is going to be no possible information gain. But typically what you want to do is have some criteria for stopping, which is a function of how deep it is. You probably don't want your tree to get too deep. It's a function of making sure that if there's only a little information gain, it's probably not worth exploring it further. An alternate strategy that people use for building good decision trees is they build the full tree so it classifies every example right. And then look for low value nodes, ones that if you kind of remove this test, it's not going to make a big difference in the prediction accuracy. Okay, and maybe get it down to a tree with 10 nodes that does the best job you can. The important point is that I think that decision tree building algorithms, these look a lot to me like hacking. It's easy for us to come up with different variants for how we would what would be our split criteria, what would be our stopping criteria. And for every one of these, you come up with a different decision tree algorithm, okay? This is kind of a different situation where, in some of the more analytical forms, we're probably unlikely to want to invent or tweak our own method. Okay, any questions about that? So what else is interesting about decision trees? Again, there's many decision tree algorithms. We can also, even use once we fix an algorithm, we can construct many decision trees, collections of decision trees, by randomly selecting which feature to split on. Note that in the tree that I had before, okay, when we had the Titanic split, the first split was based on are they male? Okay, we could have split first on the age. Okay, we could have split first on how many brothers people had. We could have split first on what class they were. Did they go for first class, second class, or third class seating? Okay, which made a big difference in survival. We can make different trees by randomly selecting which feature we use to split on at each level. Okay, we'll end up with when we end up with a different root, we're going to end up with a different tree. Okay, and again, the idea of using an ensemble of decision trees are if we can construct multiple decision trees, maybe we throw out the ones that don't do good jobs, but still, we're going to end up with a large number of different trees. We can vote on them and use the vote to decide which one is best. Okay, I mean, which class is best because it's a class that came up in more of the trees. Okay, and as I said, if you have 1,000 trees, the percentage of them that agree with the label, okay, gives us a measure not only of a label, but a question of how much we trust it. So ensembles of decision trees are a good idea. Okay, one way to build them was to split on different variables. Another approach to build multiple trees is something called bagging. Instead of building something that's going to, in each case, tree classify all n inputs, what if you take a random subset of n over 2 or square root n of the input examples, and you build a tree that works well on that example? Okay, each of these trees, because they're training on different subsets of examples, okay, will probably find certain features more or less interesting. Okay, any questions about that? It should be clear that we can build many, many trees. It should be clear that we can run our examples on many trees. It should be clear we can vote. Okay. The question that I want to bring up now is, if we have many trees, should those trees be regarded equally? The simplest thing is to regard all trees equally. Okay. But is that necessarily the right thing to do? First of all, are there any questions about decision trees so far? How this decision tree thing works? I think it should be clear to everybody how you build these trees and how you would use them, but I'm happy to listen to any questions. Okay, let's raise this question of should all trees get the votes? Suppose I have built 100 trees, and how would I judge? You could imagine each one of these decision trees is going to try to assign a label to a given example. They were trained on the same examples, or almost the same examples in the case of bagging. How should I weight these trees? Should I give each an equal vote? Or is there any other criteria by which I can decide which trees, how to weight, much to weight each tree?
You could just weight them by how well they classify everything.
So one thing that's true is that there are different trees that will classify differently, right? And, you know, so maybe this tree got a 0.9% accuracy on all the examples. This one got a 0.7. This got a 0.6, 0.8. Does everybody see that every tree has a certain accuracy on the training examples or on the evaluation examples? So we do get it, we could actually get a measure of how good each tree is, okay? Maybe we take the best tree, we give that tree all the votes and none of the others a vote. Or we could give them votes based on, you know, based on how accurate they have been. That seems like one way to do it. Any questions? Okay. Now, naturally, okay, you know, we again, the question here is still, as I said, each tree gets a vote. We could allow them equal votes, but we noticed that some trees are not as good as other trees. So the natural thing to do would be to weight them based on how accurate they are, okay? But actually, here's kind of an example that shows that there is another idea on how you weight them that's interesting. Here we have a world where there are, you know, these are the 5 different items, okay? These are going to be, the columns are going to be different classifiers. Let's say we have 5 different trees, and the stars mean it gets it right. Does everybody see on this particular example, there is one classifier that got 80% of the examples right. The other 3, trees all got 60% of the examples right. Note that taking the majority, even though all 5 of these trees did better than random guessing, if we took the majority, okay, namely gave it the label that that most of the 5 trees were, we only did 60%. So voting on these classifiers did not actually make it better. Taking the best of the 3 were not, the best of the 3 was also not the right thing to do. It turns out that if you gave equal votes to the first 3 classifiers, where you gave the first one 1/3 of the vote, the second one 1/3 of the vote, the third one 1/3 of the vote, a classifier like that was able to get 100% of the labels right. Why is it that these 3 trees, okay, together do better than the best one? What makes these 2 trees over here interesting? Why are these 2 trees that got 60% more interesting than these 2 trees that got 60%?
Because they share the most in common with V1.
What you're telling
Wait,
me,
which trees did you circle first? I'm sorry.
well, these turn out to be the good ones. These turn out to be the not so good useful ones. Even though they all scored 60%, why is it that these are better than those? The reason is because V1, the most accurate tree, already got these 4 right. These 4 examples it already got right. The example that it was having trouble with was example E. Trees 2 and 3 happened to get example E correctly, right? Whereas V1 and V2 couldn't really get anything right that the first one didn't, okay? So we certainly could weigh our trees by accuracy. We certainly could, do some kind of linear regression to maximize some kind of score or something like that. But the case of whether a tree is better or not, okay, depends on getting the hard cases right, okay? And that leads to a different class of machine learning algorithms that try to take weak classifiers, okay? If we have binary classifiers, doing 50% is guessing. Getting more than 50% means you know something, okay? Is there a way that we could combine these different classifiers? Each one of these decision trees on themselves might be weak, okay? But is there a way we can combine them to build a better classifier? The idea of boosting approaches tries to build an accurate classifier by identifying which examples are hard. Which examples are hard? The examples that are hard are the ones that the current classifier is getting wrong, okay? And the claim is that with boosting, we're going to try to weigh our examples, okay, over time to try to build classifiers that build a combination of classifiers, okay? Figure out how to weigh the classifiers so that it ends up getting getting basically all the points right eventually. And it does it by rewarding classifiers that get the hard examples right. So what is the idea? We're going to want to use weak classifiers. This, again, typically, if we just use a threshold of feature, one particular feature, is it greater than or less than something? This could be thought of as just being like a one-level decision tree. Or we could use a bunch of different trees. In gradient boosting decision trees, which is a popular thing, you take a bunch of different decision trees. We want to now figure out how much do we weigh each tree. With boosting, We're going to do it by weighing the examples over time to get more reward for classifying the hard examples right. Initially, all the points are of equal weight. What are we going to do? We are going to, one by one, add a new classifier to our mix, okay? And we are going to kind of, again, if we look at what the AdaBoosting algorithm is, we are always going to try to find a new learner, okay, a new classifier that does well on the current weighted point set, okay? We're going to measure its accuracy, okay? And then we are going to add the new classifier to our ensemble of things, where we take the, we weight that classifier according to its accuracy. The interesting thing is that at each iteration, we are going to change the weight of the points that we want to classify on the next iteration. So this algorithm is going to try to produce a weight, build a classifier from a lot of different weaker classifiers by assigning a relative weight to each classifier that we add. One by one, we're going to add another tree to our ensemble. What is the tree? We want to add the tree, the new feature that minimizes the error, the weighted error on our weighted points. The weight of our new classifier is going to be a function of how accurate it is, okay? And then we're going to go and update the weights of the points, okay? The current value of a point is going to be what? It's going to be what was the old value of a point times something that is going to, reflect how good this classifier did on, the new classifier did on these points. H of, this hypothesis, H of T of I is going to be the classifier on the given value of X, the parameter that we give it. It's going to make a classification decision. Is it a positive member or a negative member? Y sub I is going to be the label of the point. Did it belong in the positive class or did it belong in the negative class? If the classifier says positive and the point was negative, okay, we've got positive, negative times negative. That last sign there is also negative. If it's e to the negative, this thing, okay, is going to, if e to a negative number is going to, if we multiply it by e to the minus something, okay, that's supposed to make it smaller. That will decrease the weight of the point. If the exponent is positive, we increase the weight of the point. Basically, we will increase the weight of the point from what it currently is if we misclassify it with the new classifier. We will decrease it, the weight, if we got it right, and then we renormalize the points. So this is basically the boosting algorithm. Okay, we're going to go through all the different classifiers, pick the best one on the current points. Okay. Pick the best one on the current points, measure how accurate it is, add it to an assembler, our ensemble weighted by accuracy, and then update the points. So the misclassified points grow in value, the correctly classified points decrease. Any questions? If we do such a thing, we end up getting, even though all of our individual classifiers, here they were just on single variables, were linear things. The weighted sum of these classifiers defines kind of a nonlinear decision boundary, okay? And that's what we kind of want to be able to do with this. Any questions? Okay. Bottom line, boosted decision trees. These using gradient decision trees, using an ensemble of decision tree, where you use boosting to weight these trees, ends up being the most popular method in Kaggle. On Kaggle competitions, if you look at what the winning machine learning method is, it is most often gradient boosted decision trees. Okay? Boosting gives us a way to take advantage of weak classifiers. The good thing is it tries to fit every example. The bad thing is because it's fitting every example. If you have noisy data, boosting tends to overfit it. Okay? So it's sensitive to things that are noisy examples. But that said, it's still a very, a very successful method for modeling, modest-sized data sets. Any questions about decision trees or boosting or anything like that?